Hello, we are now going to talk about data collection, which is the main deal going on with our Barron's book topics 5 through 6. And so we got two major subject areas. We've got sampling and surveying, and we've got experimental design. Basically, we want to produce accurate data. And so that's what these two topics are about: collecting data, making sure that data is collected in a non-biased way. Well, there's a bunch of terminology that you need to make sure and know, and you also need to know how to describe certain procedures, such as how to randomly select, how to randomly assign, and that sort of thing. So this is going to be a sort of a quick run through of the major topics in data collection. First of all, the concept of bias. Bias just means when certain outcomes are systematically favored, and that's the big term, the big concept we're trying to avoid. We want to collect good data. So bias is when we collect data in such a way that it means our estimate is going to be away from the parameter, the true value. All right. So then we have what is known as a volunteer response. A volunteer response is one where people choose themselves to be in the sample. And when that happens, very typically you get passionate negative answer. That's why they've chosen themselves. That's why they decided to call you or to contact you, because they feel passionate about something. But the way we can fight bias in our data collection is taking a random sample. Random sample means that every member of the population is equally likely to be chosen. There's different ways of doing that. That's what a random sample means. Now, a simple random sample means you've had no grouping, no stratifying, and its specific definition is it's a sample where every group of size n is equally likely. N is your sample size. So simple random sample basically means that you've had no grouping or stratifying going on. A stratified sample is one where the population is divided into groups and some members from each group are chosen. This is best done when the groups are different in regards to the relevant issue and result in less variability. So if you look at your groups and your groups are homogeneous, in other words, if your groups look like this, and let's just pretend the variable of interest that we're interested in is the color, the proportions of colors. If you look and your groups are different, what you should say to yourself is, we need to get some from every group. We need to get representation from every group. That is what a stratified sample is, getting some from every group. And you should do a stratified sample when your groups are different in regards to the relevant issue. Now, but if your groups are heterogeneous, you look and your groups look like this, okay? They're heterogeneous, okay? There's no point in stratifying. There's no point in getting some from every group. This would be best possibly do a cluster sample where you just take one group to represent the whole, okay? So stratifying should be done if your groups are homogeneous and in other words, they're homogeneous within the group, but different from other groups. You would say, well, we need to get some from every group. And if you do it properly, there'll be less variability in results. In other words, you'll be more confident that your estimate will be closer to the true value. A cluster sample is when you divide the population in groups or a small number of groups, and you select one group or a small number of groups to represent the whole population. So if you're going to do that accurately and get good data, you need to make sure that each of the groups is, in essence, representative of the population. So, all right, so here's the first skill you need to be able to do. Be able to say how you randomly select a sample from a larger population. Sven wants to estimate the proportion of students at his school that own a calculator. He decides to take a simple random sample of 50 students out of the 2,000 at the school. Describe a method he should use. Well, since it's a simple random sample, we aren't going to do grouping. We aren't going to take 25 boys and 25 girls. Or take 12 freshmen, 13 sophomores, or something like that. So whenever you randomly select, you got to say three things. You got to clearly state that you give each one of these a unique integer. You have to state that how you randomly generate the integers, and then say it is the students with those integers that are in the sample. So you need 3 sentences. Assign each of the 2,000 students a unique integer from 1 to 2,000. Okay. Make sure you say unique or distinct integer or an integer ignoring repeats. We can't have the same person going twice. Use a random number generator to create 50 unique integers from 1 to 2,000. Say it just like that. 50 has to be unique or distinct integers, and say from 1 to 2,000. This way, all the 2,000 are equal likely to be chosen. Then state clearly the people of those integers, 50 integers are in the sample. It's not the integers that are in the sample, it's the people. So you have to say those three things, okay? That's very good chance that will be asked of you on the AP Stats exam. All right, under what circumstance would you stratify? Under what circumstance would Sven form strata made up of the grades that students are in, 9th, 10th, 11th, 12th, as opposed to gender? In other words, stratifying by grade means you get some freshmen, some sophomores, some juniors, some seniors. Stratifying by gender means you get some males, some females. Why would you stratify by grade? You'd stratify by grade if the grades were more different in regards to the relevant issue. So grades should be made into strata if they differ more in regards to owning a calculator, because that's what we're measuring here, then the genders differ. Okay, so all righty. So then Sven decides to obtain a sample by standing in the 12th grade hallway and ask the first 50 students who walk by whether they own a calculator or not. Describe the bias. All right, so the next skill you need, you have to be able to describe a bias situation. When you're describing a bias situation, you need to clearly state how your estimate, in this case, P hat, how it systematically differs from the parameter, which in this case, P. P hat being the proportion in the sample that own a calculator, P the proportion in the whole population that own a calculator. Or if you're doing a mean, X bar would be the sample mean, which is an estimate of mu. You have to clearly state systematically how you think the estimate will differ from the parameter when you're describing a bias situation. So in this case, what we'd say, 12th graders may be more likely to own a calculator because they take harder math classes. Thus, this method will likely produce an estimate, P hat, that is too high of an estimate for the population parameter P. You have to clearly state which way you think the estimate will be off and why. You have to give a reasoning there, like I did. So there you go, when you're asked to describe a biased situation. And that is, in essence, what is in the next bit of notes. When describing a biased situation, always state in which direction you think the estimate will systematically differ from the true value, or in other words, differ from the parameter. Okay, make sure and do that. And make sure it makes, and have some logic in that regard. Say why you think it is. All right, now the second big subject in data collection is experimental design. And the first thing is the concept of confounded. Confounded variables are one whose effects on response cannot be distinguished one from the other. It's kind of like if someone loses a bunch of weight, is it because they started eating better or they started exercising? Well, we don't know. And so those variables are confounded. We don't know how much of which variable contributed to the result. Okay. When explaining a confounded situation, always make clear connections between all the variables involved. And so anyway, so let's look at an example in that regard. So Linda has a relaxation program that she feels will lower the blood pressure of people who have high blood pressure. She tests this by finding 50 people with high blood pressure and putting them through the program. She discovers that almost all the 50 people have significantly improved blood pressure after the program. Discuss how confounded can be involved here. So she probably feels that her program works. She did the program of 50 people. She had almost all of them had improvement. The problem is we could have a confounded situation. This is not a controlled experiment. So when you're asked to explain a confounded situation, you have to say there could be another variable involved. And you have to explain how the variable is connected to the explanatory variable, which in this case is the relaxation program, and explain how that variable is connected to the response, which in this case is improved blood pressure. You have to connect those three variables. All right. Maybe the 50 people that went through the program started eating healthy because they knew they were being studied. So I've connected the other variable, which is eating better. I've connected it with the explanatory of the program. Okay. Maybe it was the healthy eating that caused the lower blood pressure and not the relaxation program. Okay. So I've connected the healthy eating with the relaxation program. So I've thus connected the variables. So that is a potential confounded situation. Well, what's the answer then to showing that one change in one variable is causing a change in another variable? And that's a controlled comparative experiment. a controlled experiment, comparative experiment, could help Linda show whether or not her program works or not. So what is an experiment? An experiment is a study in which treatments are imposed on the units of a study. When something is done, observational study means what the name implies. You're just observing things that happen. An experiment means you're imposing a treatment. All right. So this type of study can lead to a cause and effect conclusion. All right, if the units are randomly assigned to comparative groups. Very important to know. Very much a theme on the AP Stats exam. Our gold standard for cause and effect is a controlled comparative experiment in which the units have been randomly assigned to the treatment groups. Okay, so to write out an experiment, you have to do three things. If you're asked to design an experiment, you got to do three things. You must clearly state how you randomly assign the units to the treatment. You also must clearly state what's happening in the treatment groups. And then thirdly, you must clearly state how the results are compared between the groups. You have to do those three things. So design a completely randomized experiment for Linda. So let's do those three things. How do we randomly assign? Now, in this case, I use the hat method. You could give them all 50 unique integers, use a random generator, generate 25 unique integers, and then those 25 people, those 25 numbers get put into the control group. But I like using the hat method or the pieces of paper method because it's kind of harder to mess up, so to speak. So let's talk about randomization. Write the names of the 50 people on 50 pieces of paper that are the same size and well mixed. By saying same size and well mixed, that takes care of randomness. Okay, select 25 pieces. The 25 people whose names are on these pieces go through the relaxation program. The other 25 are in the control group and do not go through the relaxation program, but are otherwise treated exactly the same. So I've clearly stated what's happening in the treatment groups, that we have a comparative control group, okay? After the time to complete the program is over, compare the improvement in the blood pressure between the treatment and control groups. So it's important that you specifically state what you're comparing. And you want to compare the improvement. Don't just say compare blood pressure, okay? Because it's not the blood pressure we're so much interested in, it's the improvement in the blood pressure that we're comparing, and clearly state the groups that you're comparing, okay? So thus, I've done all three things there. So write it out, just like that. And then, okay. And then the last thing is blocking, all right? So blocking is, in essence, just like stratifying and sampling. You're forming homogeneous groups. Blocks are homogeneous groups that may be used in an experiment if it is believed the blocks will react differently to the treatments. All right, so if you have a situation where you feel you have reason to believe that you have groups of people or things that are going to react differently to the treatment, the response should be, we need a block on this, okay? If, for instance, you have a drug that you think old people and young people are going to react differently to the drug, your reaction to be, we'll form a block of old people and a block of young people. And within each block, do a full experiment. Okay, you can form more than two blocks. It could be a block of people over 70 years old, a block of people from 60 to 70, a block of people from 50 to 60, and so forth. Okay, but anyway, so let's look at this. Under what circumstances should Linda block on gender? She should block if she has reason to believe that the genders react differently to the relaxation program. It's very similar to stratifying and sampling. And the results of proper blocking will be less variability in your responses. In other words, you're going to be more confident that your estimate is closer to the true value. Okay, so that's what proper blocking does. So let's look at it. Well, okay, so by the way, and I didn't include this. How could she block on gender? How do you describe that? Well, if she wants to block on gender, you would say, divide up the 50 people into one group of men, one block of men, one block of women. Let's just say there's 30 men and 20 women. All right, and then within each block, do a full experiment. Take the 30 men, randomly assign 15 to do the program, 15 to not do the program, to be the control. Within the women, randomly assign, if there's 20 of them, randomly assign 10 to do the program, 10 to be the control. And at the end, compare the improvement in blood pressure between the groups that did the relaxation program and those that didn't. So that's the way you do that. And then we've got what is known as a matched pair design, which is a type of blocking where you form blocks of size 2. All right, Linda has reason to believe that people of different ages will react differently to the relaxation program. Well, our reaction to this means she should block on age. All right, she recruits 10 people with the ages below with high blood pressure to be a part of an experiment. How should she design her experiment? Now, to just do a block design, one option would be just to form 2 blocks. Form a block of 5 people, 5 of the younger people, 5 of the older people. Within each block, randomly assign, 2 of them to get the treatment, let's say, and 3 to be the control. Within the older block, randomly assign 3 to get the treatment, 2 to get the control, and then you'd compare your results. But whenever you've got a continuum like this and you're blocking on something, it's not like, let's say, male and female, or it's not, some other thing. It is, there's a continuum. Okay, you can form what is known as match pair. You could pair together the ones that are most similar in age. And so that's what we'll do. We'll use a match pair design. Each person will be paired with the one that is most similar in age. So the pairs would be 16 and 18, 22 and 23, 24 and 26, 40 with 44, 65 with 68. And then within each pair, one would go through the relaxation program and one wouldn't. So in other words, within each pair, you would randomly assign, let's say flip a coin. If it's heads, the younger one goes through the relaxation program, all right, and the other one goes through the control. And if it's tails, the older one goes through the relaxation program and the other one is the control, okay? And then you do that for all 5 of the pairings. And then after the time to do the program, compare the improvement of blood pressure. So that is what we call a match pair design. And then one special types of match pair is where one person, one entity is the whole match pair, okay? You can have, so a special type of pairs design in which one person will take both treatments at different times and see which one works better. In other words, they have a drug, let's say that they think it improves blood pressure, you give them the drug and see what happens to their blood pressure, okay? Then you take them off the drug, let their blood pressure go back to what it was before and give them a placebo, okay? And see what happens to blood pressure. Now it's randomly decided which one they're taking first, the drug or the placebo. And that is a special kind of match pair design. By doing that, you're taking out all sorts of very interpersonal differences between people, so you're reducing variability. There you go. That is a quick run through of sampling issues and of experimental design. If you have any questions, please send them to me.